So good morning to everybody. I'm happy to convene this Friday's morning session, starting with Michael Hatridge from Pittsburgh, in collaboration with Rajamani Vijayaraghavan from Tata, who will give us his third and last tutorial on basics of quantum measurements with quantum light. Please.
Hello, good morning. Thanks for sticking with me for episode 3 of this show. First, let's start with a quick review. So we're going to be talking today about taking coherent states of light, entangling them with qubits, in my case, superconducting qubits, and then what we're going to do is basically use this act of measurement to both do things we want to do for other purposes, like quantum computing and its requirement for rapid, high-fidelity QED measurement, but also to get at the essence of what these amplifiers are, what this quantum light is, and how we can both see that the light and the amplifier are quantum, that they're neat, non-Hamiltonian open quantum systems in the language of this conference, and how we can use that, again, as a tool in more exciting experiments. So just to review quickly, the system I like to consider is 3 modes. Could be whatever kind of modes you want to build them in, harmonic oscillators. And the coupling we really favor here is some coupling term that couples the fluxes phi A, phi B, and phi C of these 3 resonators together. If I convert that to the language of raising and lowering operators, then I have some amplitude out front, and I have A plus A dagger, B plus B dagger, C plus C dagger, and I get sort of a whole bunch of these 3-body interaction terms. They're in fact a lot more than I'm going to need today. And what happens is that if all these 3 modes are very different in frequency, all of these terms are going to die. So if you don't drive the system with some special pump tone, it's going to be effectively like in the dynamics, this coupling isn't there. And as you'll recall from the first 2 lectures, the trick now is to sacrifice one mode. We're not going to use this as a quantum mode in our circuit. We're just going to drive it. And if the pump frequency is very far detuned, so in this case we pump at the sum of these A and B frequencies, and that frequency is very far detuned from the resonance of the C mode, then the pump becomes stiff. It becomes a semi-classical factor in my amplifier, and basically its amplitude is going to determine how much gain I have, and its phase is going to set the phase of the transgain of my system. And you can physically implement this in a lot of systems. I like Josephson junctions. You may prefer optomechanics, diodes, optical fibers. I'm sure there are others that we could figure out. Okay, and so just to show you again spectrally, in the phase-preserving amplifier, here's the full Hamiltonian of the system. Here are my 3 modes. Here's this particular A dagger, B dagger, C coupling, which likes to create pairs of photons in the A and B mode at the cost of destroying one of the pump photons. And again, this is going to become a semi-classical stiff variable in my dynamics, because the C mode frequency here is going to be very far away from the pump frequency that I'm applying at the sum of A and B. Okay, so here's kind of a schematic, again, of the system getting a little bit more detailed. So what we're going to tend to do in experiments is to send some microwaves into mode A or to mode B, or sometimes both. And again, now there's some coupling term we're going to discuss. These are going to be coupled at rates kappa A and kappa B to these 2 output. You should think of these things as representing like transmission lines or fibers, whatever your favorite way to route signals is. And if you drive this system, then what you're going to get is an amplifier that amplifies anything incident on port A in reflection, same in port B, and sends what's called an idler copy across the amplifier with a gain root G minus 1, and again this non-reciprocal phase factor here determined by the pump phase. And the way we control the gain, which is this divergent gain right here, is to set the pump power near but below some critical pump power in the system. And if you do this all right, here's the reflection gain of a system, here's the trans gain of the system, and it just works very, very well. This kind of thing we do every day in the laboratory. So now, this being a superconducting version of this tutorial, so we have to discuss the source of this nonlinear coupling. And the ultimate source of nonlinearity in all superconducting circuits is this thing called the superconducting Josephson tunnel junction. And what it has here is a current that flows across this junction in response to the phase difference in the superconducting order parameter of these 2 big electrodes here, and it's both sinusoidal in nature and characterized by some critical current. If you stay well below the critical current, you can think of this thing as a nonlinear inductor shunted by capacitor, and now here's the Hamiltonian for the full circuit, here's the capacitive term, here's the Josephson energy, and what you get is a harmonic oscillator because, to first approximation, we can treat this nonlinear inductor as just an inductor, and then some quadratic correction that make this a nonlinear oscillator. So if you just take a Josephson junction floating in space by itself, it's going to be some kind of nonlinear oscillator. And what we're going to do is either really enhance this nonlinearity and make a qubit out of it, or make a very large junction and carefully dilute and shape the form of this nonlinearity to make something like an amplifier or some other device out of it. But sort of at the center of every fun superconducting circuit is going to be one or more of these junctions. We fabricate them in double layer deposition. This is a qubit junction here. You see it's very small. Here's the lower layer. Here's the upper layer resting across it. And in between is a nanometer or so of aluminum oxide. These are almost always made out of aluminum these days. And then here you see the really big difference in size scale here. This is a amplifier junction. It's several square microns, several square microamps of critical current. This guy here is a few hundred square nanometers. Okay, and the way we build these amplifiers in my laboratory, in particular this phase preserving amplifier that's going to be the focus of the talk, is we have to do two things. First, we have to get that coupling term I told you about, this phi A, phi B, phi C. And the way we do that is to put 4 of these junctions in a loop. So this is like a Wheatstone bridge, if you're familiar with that for diodes. This kind of cleans up the nonlinearity, and if you break the symmetry of the loop by applying some flux to it so that there's a circulating current that flows in a definite sign, you will get this phi A, phi B, phi C nonlinearity. These days we tend to cross these loops with some linear inductors. That's a detail I'll talk about in my current research talk on Monday. For now, you can just focus on these outer 4 junctions, apply a flux to it, get this coupling term, and you'll notice that the 3 modes of the circuit, A, B, and C, represent a current left to right, a current top to bottom, and then this kind of breathing mode current that comes in the sides and leaves the top. So what I have to do here is to embed this guy in a microwave circuit so that I have physical modes and physical ports that connect to these 3 eigenmodes of the JRM. And the way we do this is by having a lambda over 2 resonator on the vertical arm. You see that couples nicely to this B mode. I see I've labeled them backwards here. And then you have a horizontal lambda over 2 resonator, again putting the JRM at the current antinode so that we have the current flowing in the right way. And then we have this common mode, which I'm not going to really use. I'm just going to pump in a sloppy way. And because these are all differentially driven resonators, I have this stack of hybrids up here. You can really ignore that and just to say to you that we know how to get light in and out of these devices. So now I've got 3 modes of the mixer coupled to 3 physical modes and 3 physical ports. The kind of device I'm going to show you today, the data from is usually a little simpler these days. We basically cut off one side of the device so that it's easier. We don't have these hybrids anymore, so we just couple one port physically to the left, one port physically to the top. We pump in a not very nice way by just having a very weak capacitor here and kind of spraying light into the device. It's not really perfectly in this C mode configuration, this breathing configuration, but some of the light gets into the right mode. It's supposed to be a very strongly detuned, very strong pump anyways, so we don't really worry too much about where this extra power is going. Okay, here's what it looks like physically. This is a silicon wafer. Here you see the lambda over 2 ports. Here are the physical microwave connections going out of the box to some SN8 connectors. And again, here you can see the very big gap here that makes it a very small capacitor for the pump port. There are 2 other gaps here. They're just a few microns. You can't see them with the naked eye. We package it up with a magnet to provide the flux bias and a shield to protect it from other stuff, and we use it as our quantum limited amplifier. The gain of this system can be set to anything you want, up to like 40 dB. But if you remember the first lecture, in these systems, the gain comes at the expense of dynamic range and bandwidth. And so it turns out that the right thing to saturate our following amplifiers in most experiments is a gain right around 20 dB. So you'll see in very much of the literature, this 20 dB number, it's not because it's special or given by physics, it just turns out, depending on the kind of amplifiers we can buy to follow this thing and losses in cables and stuff like this, it's just a very convenient number. If you wanted 18 dB or 37 dB, you would just program it up. Okay, so that's the superconducting amplifier. Now I want to measure qubits, so I have to make the qubit. The way I do that is to take my junction and its self-capacitance. And again, as we discussed yesterday, I just add a big shunting capacitor. So this shunting capacitor takes the naturally very anharmonic charged qubit of a floating junction and flattens it out until it's a very nearly harmonic oscillator with a GDE transition that's, say, 5 gigahertz, and every transition above that, 200 or so megahertz lower in frequency than the one below. And so this is, of course, a mini-level system, but because all of these transitions have different energies, if I only address this one transition, I can ignore the higher states mostly. You'll see a few caveats to that, and just treat this as a qubit. Okay, and as we discussed at some length yesterday, it's a very boring qubit. It's just an anharmonic oscillator, but it turns out it has great properties. It's easy to fabricate, and so this is the system that's by far the most popular right now. And so what we do in my laboratory now is, as with many other people, we embed these. Did I get these slides out of order? Yeah. We embed these qubits in a resonator, this so-called circuit QED formalism, and the idea is we never talk to the qubit directly. We bury it inside a resonator. The resonator talks to the outside world, and we engineer, here's the cavity, linear Hamiltonian, here's the qubit, nonlinear oscillator Hamiltonian. And we engineer a dispersive coupling between them so that a photon in the cavity shifts the frequency of the qubit and vice versa with this parameter chi here. And so the name of the game is going to be to energize the cavity. That light will come back out, and its phase, the way that the cavity has shifted, will be imprinted onto the light. By reading out the light, we know the state of the cavity and the qubit. And the reason we do this is because the qubit here now is sheltered from direct interactions with this port and the outside world and can be very, very long-lived, but at the same time can be very easily read out by putting photons in this cavity. Okay. Again, this cavity filters the external environment. And so what they look like in the laboratory these days is something like a big aluminum box. Here's a sapphire wafer. Here's my qubit right here. You see the junction in the middle, this self-capacitance and this sort of big pads to give you a dipole moment that couple to the cavity to give the dispersive shift. And then basically we just put some microwave ports in here. And there's a certain subtlety that you should put the ports and structure the cavity in the right way so that you really make it very easy for light to get out at the cavity frequency and very hard for the light, the photon trapped inside this nonlinear qubit here, to escape. So we call that Purcell filtering. And at least it doesn't work this well, but if you simulate that using this silly port from the top here should allow you to have T1s in the range of hundreds of microseconds to milliseconds. Okay, here's what it looks like in the laboratory. Kind of looking, you see it's a big aluminum box with a hollow carved into it. And you look down in here you can see the cavity, this pin that determines the frequency of the cavity, and now the sapphire chip holding the little qubit. You get pretty good T1s, you control everything you like to do, and then now you put this in your fridge with your amplifier and you do quantum measurement. And just one more time to show you what a typical measurement looks like for us. These cavities often have two ports, one strongly coupled, one weakly coupled. The idea here is that any photon that enters the cavity will leave to the right, and you can drive this system in transmission. I think this question has been asked several times over the last couple of days. So in this case, what you'll get is transmission if you're on resonance with the cavity and no transmission otherwise. And again, some phase shift here. And by picking the drive frequency, if you pick where there's a large difference in either phase or amplitude or both, you're going to get a strong readout of the qubit. If you pick over to one side where the transmission is the same, you basically don't encode any qubit information in the photons that pass through the cavity, and so no measurement takes place. And here's the amplifier here. So this photon, this coherent state is going to come out, pass through these circulators, which are like the traffic cops of the microwave world, which are going to route it in. It's going to be amplified and combined with quantum fluctuations in this idle port, pass out of the system through some more amplification, a mixer, and then at room temperature, we're going to digitize this thing. And the name of the game is going to be to correlate this signal that we digitize at room temperature with the state of the qubit buried inside this resonator. Okay, so before we do it for real, I just have this nice cartoon version just to get everybody calibrated in the right frame of thought. So let's start perfectly classically. So here's my phase meter. Here's my coherent pulse that's going to enter some cavity which contains a classical qubit. Okay, so the pulse is going to enter. I've arranged a dispersive interaction between the light and the qubit so that you see the light gets a phase shift. You see the dotted lines of the old phase, it's been shifted. And now that pulse is going to travel down into my phase meter, and I'm going to say, okay, this value is G. I do the same thing again. Different phase shift for the excited state. I'm We get a different value here and record this as E. And I think this is what people think of as sort of von Neumann measurements. Is basically there are these two discrete digital values over here that correspond to the state of the qubit over here. The name of the game here, though, is that we're using these coherent pulses of light, and they have some properties that are really going to influence what actually occurs in this experiment. So let's make life a little more complicated. So let's say that the coherent pulse has some phase uncertainty in it, as our coherent state will eventually, but just still a classical case here. Then what happens is that we still get the dispersive shift, we still go into the phase meter, but now there's a distribution of potential outcomes. So this is more realistic looking already. And again, what we do here is to say, okay, there's a clear separation here. As long as these two distributions are well separated, this is very much something I can discretize to a digital sort of left or right measurement, and it's still very projective and textbook looking. The challenge in any experiment is that this phase meter, these transmission lines, they all have losses. They all add noise, let's say classical noise in this case, to the signal. So what that means is if you don't put anything into the phase meter, you're already going to get some Gaussian distribution of white noise in the detector itself. And therefore, when you run this system through again, what you're going to get is an answer that really doesn't tell you what's going on with the qubit. You kind of know that it's more likely to be ground state than excited state because clearly the probability distribution is stronger here for ground than excited, but you really don't have any idea of the state of the qubit after a given measurement. So the state of the qubit is not pure. It's not well known after this measurement process. And what you do, this is the only kind of readout you have, is you measure many thousands of times, you aggregate those all up, and that gives you one estimate of the qubit state. Yeah, this is pure classical noise that I'm adding to the phase detector. That's right. Underneath, you saw there's like, let's say, this distribution. I'm just adding to it so much white noise that I'm swamping it. And I think this is what most people think of when they think of a weak measurement. And I want to say here, this is not what a quantum limited weak measurement is. Let's call this like a bad measurement. And your intuition here is correct. You cannot dig out the information. You don't know the state of the qubit. Everything is kind of terrible. That's why we build these pair amps. Now, when we build the pair amp, and just imagine this one is perfectly ideal here. We told you a few times now that the coherent pulse has quantum fluctuations. The amplifier adds more quantum fluctuations. But everything here is perfectly quantum. And that's going to make some interesting differences that I'm going to show you experimentally really make differences in the qubit evolution for the rest of the day. So let's do this experiment one more time really quantumly. So let's prepare a coherent superposition for our initial state. And it's quantum mechanics, right? So you can't look in the box. So here's the shower curtain of quantum mechanics. And so all we can do as experimenters is send a coherent pulse in the box, look at the phase meter on the other side, and then try to do a subsequent experiment to check and see if our answer really tells us what we think it does. So the pulse enters, it interacts, your phase meter gives you a value, and in this case, the distributions are well separated, so even though you get some distribution of answers, again, this is really the quantum version of a nicely projective measurement. And sometimes you get G, sometimes you get E, it's a stochastic process because the qubit's in a superposition. But now on every single measurement, you know the state of the qubit moving forward. I think this is definitely one of the things that tripped me up as a student when I first started studying quantum measurement. It tells you very little about the past, but it tells you exactly what you have going forward, right? So if I got this particular answer, there's like students in the room. Some student tell me, not a cheating professor. What's the only thing I know if I get this answer? If I measure some unknown superposition and I measure G, what's the only thing I can conclude from a single measurement about the initial state of the qubit, about the past history of the qubit? Okay, professors, you want to help the students out? Well, no, we definitely know we're in state G, but the only thing we know about the superposition before, like the weights of these two values, is that it wasn't a pure state of E before, right? So it's very limited information from a single measurement. So you still, even with this perfect projective measurement, have to do tomography, have to measure your millions or your billions of times to figure out what's going on about this initial state. But you know very well moving forward what the future state of your qubit is. That's if you didn't know it to begin with. So what we're going to consider today is this special case where I both knew this state, I'm going to know this answer here, and I'm going to try to track the evolution of the qubit that I knew to begin with based on this additional information of a measurement. So the good weak value version of this thing is now to send in deliberately a weak pulse, prepare the same initial state, say that you know it, I'll give it to you. Now repeat the experiment one more time. It looks just like the bad measurement, but if these are quantum fluctuations, what's the state of the qubit going to be now? Sorry, a little louder? Apparently he's just talking to himself. Okay. It looks like it's about 3 times more likely than me to be in the ground state than the excited state. And if I go back and check, I'll indeed see that the superposition has been perturbed. It's now 75-25 instead of 50-50. And this is the essence that separates a weak measurement from a bad measurement, which is that a weak measurement gains a little bit of information. If I know the qubit state before, though, I know the qubit state now, and I can perfectly track the evolution from this information that I've gained. And so you shouldn't trust me. So now the next part of the talk is to basically do that experimentally. But I want to point out one other weird feature of weird measurements here before we go, which is that a weak measurement should be weak, right? But we kind of mean on average it doesn't perturb the qubit too much. That's kind of what we mean by weak. Because of course you see that these distributions on the fringes are still distinguishable from it. So a weak measurement, you can't say it only moves the qubit 5 degrees or something if it's sufficiently weak. It's only likely to move the qubit by 5 degrees. There are always going to be outliers where, for instance, you do a very weak measurement and you project the qubit. And on the converse, even if you do a very strong measurement, there's always going to be strong measurements that leave the qubit alone. And this is really a consequence of these coherent states we're using to read out these systems.
So this output looks very similar to the bad measurement output. Yeah. So you probably mentioned this already, but how can we tell if we didn't know what you've done?
Let me go through and do it for you. Like I said, don't take my word for it. So now we're going to do this with my transmon qubit, the JPC. We're just going to do the experiment. So the first thing I have to show you is that the amplifier really works. There's some hope of this being a good measurement. So the first experiment one typically does is just to turn on the readout. So this is readout. Every point here is one strong measurement, and I've just concatenated them together. And what you see here is this gray trace is one life history of a transmon. And this black trace is one other life history of a transmon. And what you can clearly see is that I can really discriminate, draw a line at 0, and say anything above the line clearly must be the excited state. Anything below the line is the ground state. There's still some fluctuations, but I can very clearly, from measurement to measurement, tell the state of the qubit and very nicely track the evolution of the qubit due to, in this case, T1. So I'm going to see these series of quantum jumps here. So that's really nice. In this case, it's like a 240 nanosecond measurement. We can do it very quickly. This qubit is nicely long-lived. So the measurements themselves, I at least can do strong projective measurements, which is good because I'm going to need them for tomography later. And so the sort of next experiment I do is to just say, okay, can I prepare the ground state? Can I prepare the excited state? And can I differentiate between them if I do? It's sort of building up to this idea of tomography and checking what my weak measurement's going to do. So here's the protocol. We typically measure once. We either flip the qubit with a pi pulse or we don't. And then we measure a second time to confirm the state. And it turns out our electronics in the computer are pretty fast. These qubits, we worked really hard to make them live a long time, but now they live too long. So my electronics are ready to repeat after 20 microseconds. My qubit takes like half a millisecond to calm back down. So what we actually do is one more pi/2 pulse to just scramble the final state. So what you'll see is an almost perfect 50-50 superposition of the initial state of my qubit, which means like half the time the experiment fails. But that's fine because my effective rep rate is 20 microseconds times 2, so 40 microseconds, which we will all agree is still very fast compared to like half a millisecond. This is starting to be like the consequence of having these really nice fast measurements. You can do these tricks. So here's a histogram of the readouts. Here's the I and the Q coordinates I'm showing you here. And now the color is how often I get these various separations. And what you see here are these Gaussian blobs like I've been drawing. And the separation here is 8.6 sigma between them. So they're really nicely separated. And if the projector's good, can you guys see here there's also a little ghost? So the qubit has a finite temperature. With a finite temperature means you have a non-zero chance of exciting the qubit to the F state. And because we have a really nice discriminating readout, you can tell it. If I take the log of this plot, so now this is a log scale histogram, you can see it's very clear. And even on this log scale plot, you can see there's very fine discrimination between these guys. So this is a really nice measurement. So what I do in practice, again, I've scrambled the qubit state. It's like 50-50 almost. What I do in practice is to basically post-select, say, okay, if this first measurement lies in this blue circle, I'm really confident it's the ground state. If it's not, throw it away and try again. And so if I do that, and now I do this second pulse here and either leave it alone or do a pi pulse to prepare the excited state from the ground state, I can show you a ground state histogram, an excited state histogram. They're not perfect, but again, this is a log scale plot here. So this thing occurs about 10,000 times more often than that thing there. And again, you can see this F excitation just kind of hanging in there. You can also see the effect of T1 and T2 kind of nicely here. The qubit has a finite temperature, but it's still pretty cold. So if it's in the excited state, it's likely to try to relax during your measurement. So you get this kind of tail here. Whereas if it's in the ground state, it really likes to stay there. You see very little smearing in the other direction. So I'm really starting to get a fine-grained knowledge of what's going on with the qubit in these short measurements. And if I just subtract these two histograms to figure out the full fidelity of this preparation process, it's like 994. I think the best we can do in the laboratory these days is like 997. So this is really a good amplifier, really a good, strong projective measurement scheme. And the reason it's so good is because it's very nearly quantum limited, and now I have hopes that when I do my weak measurement protocols, we'll really see something nice. And basically, the weak measurement protocol I'm going to show you is going to rely on these strong measurements to both prepare the qubit and to do tomography of the qubit after the fact. Okay, so here's kind of a schematic of the experiment. So I'm going to prepare the qubit along this state plus y here always. I'm going to send in some coherent state to do the measurement, and I'm going to play with the strength of this coherent state. It's going to pass through, interact with the qubit, get amplified by my parametric amplifier, and at room temperature I'm going to digitize the answer and get these overlapping distributions right here. And the whole idea that I keep hammering at is that if I have a weak measurement protocol like this and it's quantum efficient, then I will know the state of the qubit before, I will know the state of the qubit exactly after, and the information I get at every particular pixel I might land in this distribution will give me the information I need to decode the evolution of the qubit. And the thing that's going to happen if this measurement is not perfectly efficient, if I go in and then add a little bit of classical noise after the fact, is that it's going to disrupt this knowledge. So basically, the purity of my knowledge of the qubit state is going to tell me about the quantum efficiency of my measurement process. Any questions on that? Okay. So here's the full protocol we're going to run in a second and show you. We prepare the qubit by measurement because that's just the highest fidelity way I have to prepare the qubit. At the end, I'm going to do tomography here. So I only have the ability to projectively measure the z-axis of the qubit. To do tomography, I need to know x and y and z. And so what I do is basically put some pre-rotations here to rotate the information I want to measure into the z-axis. So my x and y and z tomography are just going to be rotating the x information into z and then measuring it, rotating the y information in z and then measuring it, and then if I'm already in z, just leaving it alone. And there's a lot of randomness in this process. I don't know what answer I'm going to get here. But what we're going to do is to do this thing a few billion times and to correlate each time this answer with this plus or minus one I measure and average them together to do tomography.
Sorry, maybe a stupid question, but the tomography is a strong measurement?
Yeah, so you'll see this is a variable measurement in the middle, but these two are nice and strong on the beginning and end. Just the normal sort of, there I want a projective measurement. So I get only these two outcomes here. Okay, so I'm not a theorist. I like pictures. So I have a block sphere. So I'm going to label points on the block sphere. Here are the answers I'm going to get in my digitizer at room temperature. And we're going to try to sort of give a map of how the state of the qubit on the Earth here maps to the IQ plane. So this is easy. Polar bears are on the North Pole. Penguins are on the South Pole. If I land very far to the left, I'm a penguin. The qubit has moved to the South Pole. I move very far to the right, I'm a polar bear. And I have to admit this was a happy accident, but I needed countries that are like 90 degrees apart on the Earth's surface. I'm from Texas. Almost opposite to Texas, as I learned on the flight over here, is India. And so this is the spicy food axis, and this is like the bland food axis. And so what you're going to, that joke never does well in like Pennsylvania, but I'm in the right place after 5 years of telling it. Okay, And so what's going to happen is in my phase-preserving amplifier, so yesterday VJ through me told you about a phase-sensitive amplifier. It measures only I, only Q. The first sort of perplexing thing about the phase-preserving amplifier is that it measures I and Q simultaneously. So I, in this case, told you about the Z projection of the qubit. So the question is, what does this other thing tell you? And what it tells you is basically about the evolution of the qubit orthogonal to the Z-axis. So this is basically going to spin you around the block sphere. And because the projective measurement favors the poles and has no preference for phase, what happens is you actually repeat yourself. So if your answer lands up here, you'll go all the way around the block sphere. And if it lands further up, you'll just keep spinning around. This is this thing we call this stochastic Ramsey evolution. So the active measurement is perturbing the phase of the qubit, but in a way that you know after the fact. And you're putting these two together, and now you can see here's my map of the Earth spread out to this IQ map. And it's one-to-one only in one way, right? Because it repeats itself on the Q-axis. So if I know where I am here, I know where I am there, but there are similar final states here that can end up in multiple places on this graph. But if you know this one, you can go back to that one. And so in every individual measurement, I'll land some random place, but I'll know where I am. And sorry, the other thing here is that these two back actions, this back action towards the pole and this east-west back action, are very asymmetric. And as I hinted at last time, the east-west interaction, this picking up a coherent quantum phase shift from measurement, has no classical analog. So when you ask this question of like, how do I prove I'm quantum? The active projective measurement, it's really hard to tell a weak good measurement from a strong bad measurement. But the thing that's unambiguous is this coherent evolution of the phase from this orthogonal back action. So this signal here, this going around the equator and not going north and right, so these answers that lie right along the IM=0 axis are going to be the ones who irrefutably show that there's something quantum going on, then I can use to benchmark my answers. Okay, you guys are all theorists mostly, so here's the math that backs it up. So the integrated signal here is going to give me some answer IM and QM. There's an average separation of these histograms, which is basically linked to how much amplitude of coherent pulse I put in. There's an average Q separation, and then it turns out that if I know the width of the histogram and I know the average separations, then I can decode the final X, Y, and Z state in this way. So this is basically my polar pairs and penguins in math. And what you want to notice here is that there's this other term, eta, which is the quantum efficiency. It's not maybe the one you're used to. In the normal version of Caves, he gives the quantum efficiency of the phase-sensitive amplifier at 1 and the quantum efficiency of the phase-preserving amplifier at 1. What I really mean here by this different definition is that a efficient amplifier will only amplify the quantum fluctuations it's presented with. So both the phase-sensitive and the phase-preserving amplifier in this case sit at 1. And what it actually does is just kind of change some of these definitions on the left-hand side. But if you see here, I have this nice sinusoidal signal. If I get an IM of 0, these factors are just 1 here. So I get these sinusoids, these cosinusoids, and their amplitude. All I need to know is this IM bar over sigma, which is easy to pick off just from the properties of the histogram that I measure. And then I can infer the quantum efficiency. So this gives me a nice, unambiguous, sort of one-term efficiency factor here that I can extract. Okay, so here's the actual data. So what I've done again is I've prepared my qubit in the plus Y state. Now I've done a weak measurement. I wrote down that measurement and I did tomography, and I did it, I don't know, probably 100 million times. Every bin here is the average of all the X or the Y or the Z tomogram for the times when I landed, as an answer in this bin. So this is a conditional tomography. Every different pixel here represents the average of all the times I got a particular answer. And what you'll notice here is that the most probable answer here is right in the middle. And the most probable back action, you see there's not two blobs here, right? Or maybe you believe me that they are, but they're almost right on top of each other. And the most probable back action is to leave the qubit in its initial state. So 0, 1, 0. That's the most probable thing that happens in a weak measurement, is you just don't do much. But if you, for instance, look far north or far south, even though it's very improbable, it's not even showing up here on my histogram because of my finite contrast of the projector, but I still got it several thousand times. Now I've kicked myself like 90 degrees to the right. If I go far south, I've kicked myself 90 degrees the other way. And now similarly, the I-axis here encodes movement towards the North Pole, and even though it's a very weak measurement, right, which is likely to do nothing, those rare outcomes that are far to the left and to the right project me very strongly. So you get these sort of Pepsi-looking plots twisted at 90 degrees, and everything really nicely matches the theory for these very weak measurements. That's technically enough, but if I want to show the case more clearly, let's turn the measurement strength up a little more. Now you start to see these two blobs start to really separate out and resolve themselves. And what you can see here now is that if I look right along this slice here and this slice here, I can really see that the stochastic Ramsey action is very different than the projective action. If I'm far to the left or right here, I project to the South Pole or the North Pole. If I move along this axis and that axis, I really spin all the way around the block sphere. And the fact that these fringes here have strong contrasts tell me that my measurement must be pretty quantum efficient. And this back action here, again, if you construct a purely classical version of this theory, you don't treat everything, including the amplifier quantum mechanically, you won't predict these back actions. So this is the unambiguous hint that something quantum is going on. And just to complete the picture, I should get back to the projective measurement I told you I can do. So if I just do a projective measurement and run through this protocol again, what you see is that I'm basically projecting the qubit all the time. You see here it's white, white, and blue or red. So I've projected either to a final state of 0, 0, 1 if I'm on the left, and 0, 0, minus 1 if I'm on the right. So it's a very strong projective measurement, except these rare outcomes right in the middle where I don't project the measurement at all. And if I was perfectly efficient, you would see, again, a very rapidly oscillating sinusoid right here along the center line. But my efficiency is finite. And so what's happening here is that I can always project the qubit with a bad measurement, but if I'm not perfectly quantum efficient, once I've lost a fair bit of information, the phase gets randomized. I can't track it anymore. And so these sinusoids die. And the way they die tells me again about this quantum efficiency. The other obvious thing you notice in this experiment is this like pimple on the lower right side. And again, this is not a defect. And if you look at the histogram, you can barely even see this here. This is happening, I forget, one time in 10,000. But the measurement is so good and so precise that if you, with part in 10 to the 1,000 probability, 1 part in 10,000 probability, get excited to the F state by the finite temperature of the qubit, I will definitely detect it. It's just again showing how sensitive the qubit detector is. Okay, so I can show you now in an unambiguous way that there is some quantum mechanics going on here. Yeah, so it doesn't fit in my block vector. It's definitely like an alien in terms of my conception of what the qubit's supposed to be doing. If I resolve this theory in terms of a real three-state system, then everything would be fine. It would no longer be surprising. Okay, so now what I've done here is to take some nice cuts at a convenient measurement strength here and to show you that the x and the y condition stuff for IM equals 0 are really nicely sinusoidal here. I've recorded the separation I observed in my histogram, which is a nice independent measure. I just apply this theory, and I see that the total quantum efficiency, and this is the most pessimistic way. I'm not correcting for T1 and T2, but the most pessimistic measure of this quantum efficiency is like 57%. And in the lab these days, we can maybe do best in the low 60s. So that's a really high number. When we started doing these measurements, like I'm embarrassed to say 7 or 8 years ago, this number was like 5%. Right? So we're really getting a lot better. This is really close to a quantum limited amplifier. And the other fun thing is that if you sort of do a halfway quantum calculation, if you say the coherent state is quantum, the amplifier, though, is adding the idler noise, the other half photon of noise, as classical noise, then you will run into a hard limit of this efficiency at 50%. So by really nicely breaking through this, what I'm proving to you is that the amplifier is quantum. Again, it's actually squeezing these two input lights together. So what it's really doing is generating three-body entanglement between the qubit, the signal which would I entangled to it. These were entangled by the dispersive interaction. Now the amplifier is actually entangling these other two bodies together. And so the trick is that the idler fluctuations, they do affect the qubit evolution. They make the qubit go left and right. But they're not noise. They're not classical noise. They're not obscuring the signal. They're changing the quantum evolution of the qubit. And that sounds weird, and it should. You have a question?
But you'd still like it to be as classical as possible, so this didn't happen, but a good classical.
No, I want this to be quantum, because now what I'm going to do is say, oh, that's interesting. You see, it entangles whatever's in the idler with the signal, and I'm going to use this to try to do remote entanglement. So I'm actually going to use the squeezing operation of the amplifier to entangle light together. If I've pre-entangled the light with some qubits, I can now remotely entangle qubits by measuring them, which is the next part of the talk, remote entanglement via joint measurement. And now I think I have time. I'm going to do this nice and slowly 2 different ways. The first way was done by me at Yale, and the second way was done by VJ. So here's the first time, entanglement via 2-mode squeezing. Okay, so now the system's a little bit more complicated. We have 2 stationary transmon qubits. Let's call them Alice and Bob. And in this cartoon here, let's imagine we have 2 flying spins. So don't think physically, just think 2 flying 2-level systems. We'll call them Arnie and Bert. Bert's going to be entangled with Bob. Arnie's going to be entangled with Alice, and then they're going to fly away off to some measurement apparatus. So these are flying, these are stationary. This is a very standard 2-qubit remote entanglement protocol. What I do is I first take Bob from G to the superposition of G plus E, so I put him in a maximally superposed state. I take Alice, I put her in a maximally superposed state, and now I'm going to run, this is a 2-qubit quantum gate, which I haven't discussed at all. It's basically a unitary manipulation of these 2 that's going to flip one if the other's in the ground state, and not flip it if it's in the excited state, for instance. And so this gate sounds very nice and classical, but if the control bit is in the superposition, then what it can do basically is to now entangle Alice and Arnie, entangle Bob and Bert. So after these 2 C0 gates, I have the upper half of this diagram entangled, the lower half of the diagram entangled. So these are 2 Bell states where one half is flying, one half is stationary, but they're not entangled with each other yet. So then what I do is I entangle the 2 flying qubits with each other with another C0, and now I have 4-body entanglement. I'm going to measure to resolve that entanglement, and then I'm going to measure in this particular way that I measure the X value of this qubit, I measure the Z value of this other qubit. They're now destroyed, but the 2 qubits that stayed behind are now in one of these 4 Bell states. Okay? And what's going on here is that this measurement will tell me the sign of the Bell state, and this measurement will tell me the parity of the Bell state. So if I measure that this one is an even parity and a plus sign, I'm here, and so on. There are 4 possible answers here, each of which encoding one of the possible Bell states. And you might not like this protocol at first glance because it turns out, it's not deterministic, it's stochastic. I don't know which one of the 4 Bell states I'm going to get. I just know I'll get one of them every time. It turns out in quantum computing, this is not a big deal. I can either record this answer and then very quickly apply a unitary to rotate them all to the Bell state that I want. Or often what I can do is just tell my thing that's controlling the quantum computer to rotate some subsequent pulse to take this into account. So these kind of protocols here where you always generate a Bell state, but there's like some variety, as long as you know which one you've generated, the protocol is considered perfectly successful and happy. Okay? So this is a little bit complicated now. I need C0s here. And physically, as an experimentalist, I need 2 different kinds of C0s. I need a C0 between a stationary qubit and a flying qubit, and a C0 between 2 flying qubits. And they're the same matrices in our theory, but they're typically different hardware in the laboratory. And I need these single-shot measurements. The other thing about this protocol is that even though I generate a Bell state every time, if these are not good measurements, if these are not high-fidelity measurements, averaging over these different Bell states will destroy the entanglement, right? So this is not a protocol where you can average many times together because it generates 4 different Bell states. If you average over the 4 different Bell states, it's not entangled anymore. It's just some ugly thermal state. So this is the thing I want to do in the laboratory as the next step. And there's 2 complications. Number 1 is I don't have flying spins. I mean, I guess I could fling transmons through my system. That would be very expensive. I have coherent states of flying light. So I have a different physical system here, which is going to add wrinkle number 1. And wrinkle number 2 is I need this kind of entangling gate and this kind of high fidelity measurement here. Okay? So how do we do this in our superconducting system? So here we're going to use coherent states. And now it turns out that we can solve many of these problems. So we now know that we can transmit these flying qubits, these flying quantum states pretty well. I showed you in the last experiment. I've shown you that we can do pretty quantum efficient measurements here. The third piece is basically how do we entangle them. And the nice thing is that we would suspect a quantum limited amplifier would do this part right here. It turns out this particular phase preserving amplifier I'm using, the JPC, will also do this part. Because we tried to, I showed you on the last slide, this very high quantum efficiency weak measurement shows that it's really squeezing and entangling these two coherent states of light that are entering into it. Okay, so here's now the modified protocol. Now, Arnie and Bert are coherent states to start the protocol. Alice and Bob are transmon qubits in their ground state. Again, I prepare a maximally superposed state. I have my dispersive interaction that we've been talking about throughout. And now I've entangled the upper two. I've entangled the lower two. The act of measurement and entangling of these two flying qubits is going to be undertaken by the Josephson Parametric Converter, by the amplifier itself. It's a different kind of amplifier. Its outcomes, right, are continuous. And I get these two different values. But it turns out that these two different values, the first one is kind of like the parity info, and the second one is mostly like the phase info. And of course, the math is more complicated, but if I apply this Krauss measurement operator correctly, then basically what can happen is that my final state can be an entangled state of these two qubits who never interacted directly with each other. And this is both a really cool physics experiment, and it's a really useful quantum computing task as well. There are a lot of quantum communication protocols, or what are called modular quantum computing protocols, or remote or remote or teleported protocols that rely on this ability to have some flying carriers of quantum information that we can use to entangle fixed distant objects. So it's both a fun experiment and it's useful in superconducting quantum machines if we can get it working. Okay. So skip that for now. This is what it looks like. Okay, here is a cavity and a qubit, and here is a cavity and a qubit. And what I'm going to do, right, if I were to erase this right-hand side of the slide, this is exactly the scenario we've been showing you before. We're going to read out this qubit here in reflection. It's going to enter the amplifier, come out, be digitized. This is exactly the scenario I've been showing you before. All we're doing now is adding the second qubit on the right-hand side, which we're going to read out at the same time. If I were to read out just one or just the other, I would be right back where I started with the single qubit data that I've been showing you all along. The trick here is that I'm going to read these out together. And one of the things I've indicated here that is a little confusing at first glance is that this qubit is at 7.5 gigahertz. Sorry, cavity is at 7.5 gigahertz. This cavity is at 9 gigahertz. So I've got a 7 gigahertz coherent state and a 9 gigahertz coherent state. You really don't expect, if you put them on a beam splitter, they wouldn't interact, right? They're different frequencies. The sort of interesting thing about the JPC is that I'm pumping, of course, right, at the sum of these two frequencies. So one of the interesting properties of this amplifier is that when I send in 9 gigahertz light on this side, it will get reflected as 9 gigahertz light. That's fine. We're just going to throw that away. But it'll also get transmitted and come out as 7 gigahertz light. So this two-mode squeezing operation of the amplifier is both interesting because it squeezes light from two different ports, but it also squeezes light from two different frequencies. So that's really cool. It turns out to be one of the hardest parts of the experiment in practice because here you have an amplifier that has some imprecision in which frequencies it links. Here you have two fixed frequency cavities. And so one of the hardest parts is basically engineering this whole system so that all the frequencies line up. It turns out the most important part of this thing is that they're big aluminum cavities and we can shove screws in them. So the way the experiment works is that you cool it down, none of the frequencies match, but if you put a screw in the cavity and displace some of the metal wall at room temperature, you can kind of predict how it's going to displace the frequency of the cavity cools. You cool it back down again with the screws. 1 or 2 tries later, you've put everything together in a nice enough way that you can measure and have some success. Okay, any questions about that? You guys are quiescent today. I've worn you out over the last 3 hours of talking. Okay. And I'm going to massively simplify things here. Now, if I want to calculate correctly the evolution of this system and do all the math in the quantum way I should for these open quantum systems that I'm dealing with, it's a big, nasty stochastic master equation simulation. And we published a nice PRA here from this guy named Matti Silveri, who was a postdoc for Steve Gerwin, who basically figured out that the sort of semi-classical picture we like to use as experimentalists, I'm going to show you here, is basically correct. And if you do the full details, it's still correct. And it has one other nice feature, which is that after we simulated it on a cluster, we figured out that you could actually solve these stochastic equations. Don't ask me, but I think some people in the audience will nod when I say something about stochastic calculus. So this is actually, you can get a closed form, fully quantum version of this calculation, but I'm going to stick with my nice lollipop drawings here. So again, just to emphasize what's going to happen in this system, if I send in a signal to the signal port alone, it's going to be amplified at the same frequency. It generates an idler copy. I'm going to throw that away. If I drive the other port alone, again, it has a reflection gain. I'm going to throw that away also. Because it's a two-mode squeeze state, there's no advantage for measuring both outputs. They're correlated down to the last half photon, which will be obscured by added noise anyways. So as long as I measure one of the two outputs, and you can pick whichever one you choose, you're perfectly free to throw away the other one without gaining any more or losing any more information. And again, because I'm driving at this difference frequency, these two input frequencies, which are very different, will get combined into one two-mode squeezed output at the same frequency. And if you want to think about how they sort of, the centers of these lollipops move, the amplifier just kind of adds them. So if you send in these two things, and they sort of add, they each are head to tail, it'll basically add in the amplifier. If you send them in opposing, they'll add to 0. At quadrature, they'll add in quadrature. So it's really like a coherent addition of these two input coherent pulses that start at two different frequencies but end up at the same frequency.
Sorry, could you explain again why throwing away the idler doesn't degrade your scheme? Like,
yeah.
I would imagine you're entangling the system now with an environment.
Right, but so I want to entangle it.
But it's at 90 degrees somehow, is that?
It's, yeah, remember I had a diagram last time of this, or 2 times ago, of this two-mode squeezed light. So the information of the output of one when I digitize it will be correlated down to the last half photon with the answer of the other. There's a certain correlation, but in terms of just digitizing and recording the answer, I just need the fact that they're correlated. It is true, you know, that there is a certain imprecision here, right? That these two-mode squeeze state is not perfectly correlated. It's not allowed to be. But it's as correlated as quantum mechanics allows. And in real life, I'm going to have following amplifiers and all sorts of other defects that add way more than an extra half photon of noise. And so what's going to happen is that measuring these two things, I won't get any added precision. And in reality, you know, I could, and you could say something about trying to average out the classical added noise, and there might be some advantage there depending on how noisy your following system is. But it requires twice the amount of output hardware, and your professor doesn't like to pay for that much, so you just record one, and you throw the other away. Okay, but the key thing here is that when I read out these 2 qubits simultaneously, the amplifier will just sort of add them in this, again, you know, here are the real details, here's just like a nice picture to explain what's going on. And so there's sort of 2 kinds of readouts you can do in this system, and it's really neat that they have very different back actions and behaviors. If you put the 2 systems so that they're like 90 degrees out of whack with each other, then one comes out as 4 different answers. Basically, you can set it up so that here will be the GG, here will be GE, EE, and EG. And you see you have this nice thing where every one of these answers lives in their own quadrant. You can kind of digitize this thing by quadrant, and what you'll get is a 2-qubit, 2-bit joint readout. So in a single shot, you'll learn the Z information about qubit 1 and the Z information about qubit 2, and therefore also their correlation. So it's actually perfect for tomography. If you sort of dig into the quantum details of this measurement, I've written here that you see, like there's everything here is kind of used twice. If you look very carefully, the I-axis, as I've been describing it for the signal qubit, is the Q-axis for the idler qubit, and vice versa. So if you do a weak version of this thing, the 2 qubits will evolve in a correlated way that if qubit 1 goes left, qubit 2 will go up. And that sounds like it should be exciting, but it turns out it's a correlated evolution that never generates entanglement. So this one, it does nice things for our tomography. It's no good at generating entanglement. But the key thing that we really enjoy here is that we measure in a single shot, independently of each other with no extra hardware, the 2 qubits as if the other one wasn't there. And so now instead of having to do 15 or 16 different measurement axes and complicated decoding, we measure directly the tomography we want on a single shot correlated basis. And if you do 9 different detector settings, you measure the 9 correlations and you get the 3 and the 3 single qubit pieces of information for free. So it's just showing that basically the 2-mode squeezing is not a panacea. If you put the 2 inputs into the system the wrong way, it won't manage to squeeze the 2 qubits together interestingly on the output. But it will let you do tomography. That's good. Where's the other one? Sorry, something's out of order here. So now, the other thing I can do is basically rotate this second qubit around. So let's imagine I've taken the first qubit, I'm reading it out in the usual way before, where the 2 bobs are separated on the I-axis. So this encodes the Z information, this encodes the stochastic random Z-back action. And so my 2 choices here are basically the one I told you about before, and I put this one at 90 degrees, and if you just add the red and the red, they go there, the blue and the blue, they go there, and so on, I get this joint readout, where I'm just adding each of these inputs to get these outputs. But then the other thing I can do, here's what it looks like in the laboratory. Okay, it's not quite as perfect as what I showed you before, but you can very clearly see that if I just digitize this and draw lines between these, I will get a very high fidelity single shot readout of these joint information of these 2 qubits. And then to do the entangling style readout, turns out what I'm going to do is basically rotate the second qubit to try to get a different scenario. Because what I don't like here is that, if, for instance, if I want to create an even parity Bell state, the fact that I get one answer for EE and one answer for GG and they're very discrete from each other is no good, right? In a true parity measurement, these 2 guys would give the exact same answer because I want to know that I'm definitely not in those guys, but I'm definitely in these guys and I have no idea where. One of the interesting things about entanglement by measurement is you don't want to gain too much information. You want you or any other observer to only be able to conclude, yes, I'm in this subspace. No, I don't know where. So what I'm going to do, turns out here, is just rotate this guy by 90 degrees. Again, I'm going to add them in the amplifier. And what happens here is you see this blue ball add up to give you, for instance, GE right here in the middle, centered on the origin. And this red and blue ball add up to also give you a blob right here in the origin. And you see that the EE answer gets displaced strongly to the left, and the GG measurement outcome gets displaced strongly to the right. So this won't always entangle me. Sometimes I'll know that the qubits are now in the state GG, and sometimes I'll know that the qubits are now in the state EE. These are product states. These are not exciting. But if I land in the middle, I will know that I have landed in this subspace, and I don't gain any extra information that's going to mess me up. A natural question here, though, to ask is this Q thing. In the single qubit case, it encoded this stochastic Ramsey kind of operation, which was not, in that case, any problem. It was actually very exciting. But here, what's going to happen here is that it's going to do something similar in this case. You're going to land in the GE and EG manifold, but this extra information is going to kick the phase within the manifold. So all the states that lie in the middle of this thing here are going to be odd Bell states, but their phase is going to be perturbed in such a way that I can't throw this Q information away. I have to record it faithfully to know the state of my qubit. So that's not ideal, but this is sort of the consequence of the way we've chosen to try to implement this measurement. Okay, so now basically if you look at the success of the fidelity, this would work half the time. You'll be in some Bell state, you'll have this stochastic phase shift, and again, it's okay. You can fix it later if you need to. So now going back to my out of order slide. So here's the protocol I'm going to run. I'm going to once again prepare the 2 qubits by measurement, that same joint measurement I showed you before. I'm going to apply pi over 2 pulses, just like in the protocol at the start of this section, to create maximally superposed state. Oh, I'm sorry. This is a more fancy preparation sequence. This is going to create the maximally superposed state. Here's now some variable strength measurement where I read out the two qubits together. And the thing to realize here is that in this case versus that case, again, I'm rotating the drive of this cavity to either do the joint projective measurement or the entangling measurement. And then here, I'm going to do my 9 different detector settings, basically X, Y, or Z here, X, Y, or Z here, tensored out. And I'm just going to run this protocol over and over and over again to try to generate the data that I've showed you before. And just to show you that this is not a hallucination, here's what it looks like in the laboratory. And you see that this one is twice as bright as these two, and I can nicely separate them, so at least I have some hope to continue onwards. Okay, so now there are 2 caveats here that I wanted to go through. So I think most of you don't do tomography every day of your life, but when you have 2 qubits, right, you have I, X, Y, and Z for one qubit, I, X, Y, and Z for the other qubit. That notionally gives you 16 parameters that you need to measure to get a full knowledge of the qubit state. One of them, this I one, is the identity. It's kind of for free. And so if I now want to tell you about the tomography and to show you which axes are really telling me something interesting, if I have a maximally superposed state, which is what I start with, I'll start with information in YI, IY, and YY. And if I add and square these things, it turns out any 2-qubit pure state, these 3 Pauli vectors, or however many it have, will add and square to 3. So what I'm looking for in a pure Bell state is something with 3 values, but nothing in the qubit sector. Basically, qubit 1 can contain no independent information. Qubit 2 contains no independent information. So when I transform my initial state into like a Bell state, what you'll notice here is that this ZZ thing, which defines parity, has no definition for this unentangled state, this particular unentangled state I've chosen, but for the Bell states, 1, 2, 3, 4 different Bell states, it will definitely have a parity, either even or odd. And now, as I showed a little while ago, it'll also have these other 2 pieces of information, which are just redundant copies that tell you about the sign of the coherence. So when I do tomography, what I'm hoping to find for any given Bell state is one, if the Bell states are of this form, one with a definite parity and a definite sign. So I'm looking for one of these answers, basically -1, +1, +1, etc. So what I'm going to show you moving forward are kind of these kind of tomographies to show you what's going on in the Bell basis. Okay, so now I have a picture. Yeah, out of place, there you go. And so if I want to describe in general how this measurement's going to work, there's 16 states. It's very hard to draw, right? I don't have a block sphere anymore, but I do have this IQ plane of answers. And if I just pick out some important states, so here's GG, here's EE, right? These are definitely 2 of the 3 blobs in my entangling measurement. And now here is the odd parity Bell basis, where I've picked out 4 cardinal states, minus, plus, plus I, and minus I. And actually, it turns out the back action of the measurement is going to kind of create the same map I had before. Just to say one more time, if you land in the middle, if IM is nearly 0, you're going to be in some kind of Bell state. And then you'll look along the Q-axis to figure out what kind of Bell state that was. Okay. All right, so here's what the data actually look like when we run this protocol in the laboratory. So here again is the histogram. Here are the answers in the middle, answers on the left and right. Here's the ZZ tomography, again conditioned on all these different answers. And what you see is that GG and EE have a definite parity. And in the middle, you get the opposite definite parity. So that's good. That's one of my 3 Bell components of the block vector that I'm looking for. The other ones, however, for instance, like XX, contain no information. They're white here. And I say, oh, well, did I leave that information in the single qubit sector? And the answer is no. If you look here, this is basically white also. But what's going on is this efficiency of entanglement is not high enough. So even though I'm sort of doing the right maneuvers, what's going on is that this stochastic back action on the phase is getting averaged out. By the time I've projected the parity to be strongly, in this case, -1, I've destroyed the phase of my Bell state. So I never really get to an entangled state. I sit right on the edge with a state, a nice separable state that's a thermal admixture of GE and EG. And so this is frustrating. And in fact, there's a new version of this experiment that's a little better, but still maybe not above this bar of generating entanglement on the archive. And so what do we do? So we go back to this idea of taking inspiration from weak measurements. So what we're going to do, and this is going to happen in the other remote entanglement protocol I'm going to show you in a moment, is we're going to turn the measurement strength down, because we want to generate entanglement, and our metric is to say that we sometimes at least generate good entanglement. And we're happy to trade the probability of entanglement for goodness. And the answer, it turns out, is not to be more projective, sort of as you'd naively expect, but it's to trade against losing information versus gaining projectivity by sitting at some sort of maybe not very weak, but maybe medium strength measurement. So what I'm going to do is turn the measurement strength down. Now you see that my three blobs are not really separable from each other. And if I now look at the ZZ tomography, you see here in the middle, it doesn't quite go to -1. And you see now a smooth transition to +1 on the outside of this thing. But now the other very encouraging thing is if you look carefully at this graph, you see it goes from red to white to blue to white to red. So I'm getting this phase information back here, and I'm starting to see this stochastic Ramsey, which I should always see in this measurement when it's working. And again, for these answers very near the middle, I've destroyed the single qubit. I've projected the qubits out of the sort of single qubit information basis and into some sort of very close to an entangled qubit basis. And it turns out when you work through all the math here, we're still sort of not there. This 60% quantum efficiency that we have is not enough to make this protocol sort of break even. It's a little bit like entanglement purification, if you're familiar with that. In entanglement purification, most of the protocols that you have a finite initial entanglement below which they basically just don't work, and above which they'll generate better entanglement. So this one is trying to entangle, it's losing a little bit too much information, even this sort of modest phase. So even though I've cut the projectivity down, I haven't gained enough on the phases to make it work. But if I just sort of convince myself that everything is behaving correctly by looking at these coherences and looking at the way they oscillate and looking at the way we generate entanglement, everything makes sense and matches my theory. And I can extract some efficiency from this, which I think was like 50-something%, and it's just not high enough yet. So this is kind of where we are with these kind of experiments. And we have some new ideas in the laboratory, and we're continuing to work on them. But we can definitely prove that in the single qubit readout, we can see this sort of quantum nature of our amplifier and the implications for qubit evolution. We'd like to use the entangling nature of this amplifier as a tool. We're just on the edge. So now, in the final 15 minutes, I want to tell you one final piece. This is going back to an experiment that VJ did. So what I've done is sort of entanglement the hard way. I've used this not perfect quantum object to try to entangle my light. Turns out another way you can do it is via sequential measurement, which is to say that if I take my light and I interact it actually in the exact same directional cascade that Ash showed yesterday, I can basically engineer pointer states that will be entangled sort of before they go into the amplifier. And then if the amplifier is not so perfect, it doesn't really matter. And so this experiment, I think his name was given by Hideo Mambuchi, goes by the name Bounce Bounce, as you'll see why in a second. So this is just repeating what I have just said. So what we're going to have here is two cavities, two qubits, and the trick is going to be to drive a coherent pulse to the system that first bounces off 1, picks up information about qubit 1, then bounces off qubit 2, picks up more information, but does this whole thing in such a way that now you, the observer, with ideal, even if you're an omniscient observer of this light, you can tell, for instance, the parity of the system, but you can't tell anything anymore about individual information on qubit 1 and qubit 2. And the key difference between what I just told you before is that here I'm engineering the light before it gets to the amplifier using this sort of circuit QED architecture. The amplifier could be phase preserving, could be phase sensitive, doesn't really matter because I've hidden all the single qubit information before it ever gets there. So the key thing here is going to be basically losses before it gets to the amplifier. And this was proposed, I think, a while ago again by Hideo Mambuchi. So here's the experiment. Here's the publication. Basically, I'm going to put light into the system here. The circulator is going to impinge it on qubit plus cavity number 1. It's going to pass out through a... They wanted to make it remote, but I don't know if you've seen a dilution refrigerator. They're pretty small. But they made it more remote by coiling up a meter of cable. So they're like, look, they're a meter apart. I think in the actual experiment, they were like an inch apart. But the light traveled as if they were a meter apart. Impinges on qubit plus cavity 2. Now, at this point, it's a parity measurement. It passes out through whichever paramp you choose here, and we're going to digitize it and show that we've made entanglement. So I've added this one slide here to try to show you, at least in words, how this works. if I send in my light here in some boring unentangled initial state, and I think about what this interaction does is to basically pi phase shift the coherent state if the qubit's in E, let's say, and do nothing to the phase if the qubit's in G. Then I'll see, here's the light. Now the light is entangled with the qubit. I've colored it blue and red to indicate this. If the qubit's in G, you'll get this answer. If the qubit's in E, you'll get this 180-degree shifted answer here. And the key part of this protocol relying on is that 2 pi phase shifts is the same as no phase shift. So now this light, which is entangled with the first qubit, hits and interacts again a second time. And what happens is, if it's in G again, no rotation, so you stay right where you started. But if you're in E and you started over here, you get another pi phase shift and land right on top. So GG and EE give an overlapping set of answers. You cannot, by telling where by getting any answer in this distribution, you don't gain any information about GG versus EE. Similarly, if you pick up a pi phase shift from qubit 1, or you pick up the pi phase shift from qubit 2, so GE or EG, again, you lie right on top of each other. And so what we've done by engineering our circuit QED interactions is to generate something that's really what we would call a parity measurement. That is, all outcomes on the left have odd parity, all outcomes on the right have even parity, and all I have to do is deliver that state intact to the amplifier, amplify it efficiently, and I'll get a perfectly nice entangling measurement. Okay, now the problems are there's losses here, there's losses here, this phase shift may not be exactly 180 degrees, right? There are a lot of imperfections. And the name of the game is, just like I showed you before, to get to a projective parity measurement before you lose all your phase information. And so, just as I did, they're going to play with the time, or you can think of it as the strength of the measurement, and now they're going to measure concurrence, which is a basis-independent way to measure whether or not you're entangled. And so here you can see if they don't measure at all, they have this maximally superposed state. As they start to measure, they start to get the bars indicating the parity. These two guys go up, but the coherences here and here go down. So there's a competition between becoming a more projective parity measurement, but having someone in the universe gain enough extra information to destroy the phase of the system. So here they say they're SNR limited. What they mean is they're not projective enough. Here they're loss limited, which is to say that their projectivity is not really increasing anymore, but they're still losing phase information. And right here in the middle is some sweet spot. And basically by generating this positive concurrence here, they can show that they are definitely entangled and they have some decent fidelity. I think it's, this is not my experiment, but I think in the 50 to 70% range. So not perfect entanglement, not 99%, but very measurably provable entanglement in the system. And so what these two measurements show you kind of together is that, at least in these superconducting systems, we can generate quantum light, we can entangle it with our qubits, we can start to manipulate it both outside the amplifier and inside the amplifier in meaningful ways. And we're sort of on the verge of being really able to show you that this light traveling through our system is like a qubit. It's not a stationary qubit, it flies and dies. But we can start to manipulate it, we can start to imagine to control it in more sophisticated ways, and really then to work on the light to entangle the stationary qubits that are left behind. That's kind of the long-range dream of a lot of this work. Okay, so the parametric amplifiers themselves, they're nearly quantum limited. Most of them today are used just to do projective von Neumann style measurements to enable this rapid single-shot QED measurement that you require for basically error correction, state preparation, readout of your quantum computer. That part works really well. Like I said, we can do 994, 997. Everyone has, I think, at least 1 9 these days, and their experiment is working on 2. We can keep quantum light coherent in the system sort of almost long enough to do some of these more exciting things. Exotic measurement operators, remote qubit entanglement. We're not quite there yet, but we're going to keep banging on the door. And then to sort of advertise my own talk, the scientific talk on Monday, but this is not to say that these amplifiers are perfect, right? In addition to this imperfect quantum efficiency, they have limited bandwidth, they have lack of directionality, they have lack of dynamic range. You can't process a lot of information in them at the same time. So we're also sort of banging on that door and trying to solve these problems together and just really work into a scenario where we can do all the interesting and fun quantum measurements we want to do to enable quantum computing, but also just to have fun. Okay, here I think I'll stop and take any questions you have left.
Okay, and we are ready for some questions. Yes, there, up there. No.
So you mentioned like there's a weak measurement versus a bad measurement, right?
Yeah.
So I guess if you, when you send your microwave, let's say if the phase is not sharp.
If the phase is not well defined.
Yeah, supposing the input microwave doesn't have a sharp phase, then I guess you would have like two broad distributions, right?
That's right, that's right. You get like this kind of, if your amplifier, like if you measure over a second or 2 seconds and your phase drifts in that time, instead of this Gaussian blob, you get this kind of banana-shaped thing. If you have amplitude noise, it'll similarly mess up your distribution. So we definitely worry a lot about stability of the amplifiers and of the generators of light themselves. And we worry about someone flicking a cable and changing its electrical length. Most of these experiments are built as interferometers. So in the phase preserving amplifier, if your phase drifts but you have sort of a reference copy, you can undo it after the fact. So in my phase preserving protocols, the whole system is built as an interferometer so that you're protected against everything but basically drifts inside the fridge. Those are your signal. But if the generator drifts, then my digitizer just drifts with it and can correct for a lot of these errors. In VJ's phase-sensitive amplifier experiments, this doesn't work. You can't sort of passively correct because the amplifier is designed to amplify one quadrature and destroy the other. So if you go in with the wrong quadrature, there's no digging the information out on the back end. So in those phase-sensitive amplifiers, you have to sort of actively correct and feedback the light to keep the phase nice and stable, otherwise you'll get some additional it's not sort of the same kind of quantum problem, but it's definitely like an ensemble problem, that the ensemble will just drift over the experiment and you'll get distributions that are all smeared out.
Okay, when you say it's a bad measurement versus a weak measurement, that's not completely clear to me.
Okay, well, so let's imagine that you just use a commercial amplifier, like a HIMT amplifier from one of the vendors. Those have a quantum efficiency of like 2%. If I put in we can describe them as sort of losing 98% of the light that passes through them. If I put a lot of light into such a system, I will get what looks like a very weak measurement. So if I start out with a sort of strong measurement, so these widths are now the widths enforced by quantum mechanics on a coherent state, but I just add lots of noise. What I get is sort of two strongly overlapping histograms. That's very different than the scenario where the histograms overlap because I engineered the quantum mechanics too. Maybe one thing that helps this make sense is that I don't usually know the round-trip gain in my system very well. We attenuate by 80 or 90 dB going in. We amplify by like 90 or 100 dB going out. So I don't have an a priori knowledge of the voltage that would help me tell the difference between these two. What I usually do is just measure the separation and the sigma and try to extract information from it. So if this separation over sigma looks like that separation over sigma, I don't have the tools to a priori tell the difference. But the qubit back action here, this is a projective measurement. You add classical noise until you erase the qubit information. Whereas this one never carried a lot of information out of your system to begin with. So the sort of back action is very different. But just by looking at the histograms, which is sort of the easy thing to do experimentally, you can't a priori tell the difference. Does that answer your question a little better? Okay.
Any other questions? Yes, please.
Along a slightly different line, what's the potential for scalability in these kind of systems?
Well, you just buy more amplifiers. It's like my favorite kind of scalability. I guess so the answer there is kind of long. It really depends on sort of engineering details. If it costs $1,000 per qubit and $10 per amplifier, then I will just have 1 qubit per amplifier. If it costs $20 per qubit and $1,000 per amplifier, I need to figure out how to multiplex the amplifier and stuff like this to make it scalable. So in many of the sort of 4-8 qubit experiments, they just brute force it. Just and they just brute force it out. But no one has like a well-conceived notion of what 10,000 qubits will look like, so I can't tell you where the sort of economics will.
So you can use one amplifier can work for many qubits.
So we would like it so that one amplifier could work for many qubits, so that, for instance, you could spread the qubits out in frequency space, and if the amplifier was broadband enough, it would just amplify them all.
I see.
And for instance, VJ has a recent publication where I think he's doing 3 or 4 qubits that way. The problem they run into, A, is, like I said, they have limited bandwidth, and B, they have limited dynamic range. So first, it's hard to fit them all in, and then when you do, if you read out 4, it'll just saturate. So this is something we're sort of actively working on, and I'll talk a bit on Monday. There are more sophisticated parametric interactions, more mode amplifiers. It's a little bit harder to pump them. Let's say you do this, you invest a little bit more in the amplifier hardware, but now you could handle 10 or 20 qubits per amplifier, then it's a net win.
And how about using more states on your qubit?
Okay, yes, you mean using QDITs.
Yeah.
So you saw my amplifier would be perfectly happy to read out like a 4-bit QDIT per amplifier, right? We nicely separated those 4 blobs. What that means for your quantum architecture is a whole other question. So I could read that out, but last time I checked, people were not eager to re-engineer the surface code with you know, Q quads or Q trits. So there are things that the amplifier can do that only gain value if they help the sort of quantum architecture do things it already wants to do. I mean, if I was building a quantum computer with my own amplifiers, one thing I would do is to use both sides of the amplifier. I've showed you can easily read out 2 qubits at once, so that would be half the number of amplifiers, right? That's kind of a no-brainer given this. You know, how you make that 10-time improvement, 100-time improvement, and whether or not that helps, I don't know. And it's a whole other conversation, the economics of how you scale up your quantum computer. I mean, it's a little bit mean to poke these guys on this because it's like asking someone like with their, you've seen like the Schottky diode, which is like the 2 pieces of silicon jammed together, right? It's like asking those guys what the Pentium is going to look like. There's tons we don't understand about architectures and scaling and 2D qubits and 3D qubits and how much a control channel costs. And those things will influence evolution going forward, but they're all question marks. The one thing I'm pretty sure of is that there's not a competing technology that is not parametric to drive the amplifiers to do these readouts. It's going to be, you know, some kind of parametrically driven process, I'm pretty confident, that drives this thing. You're not going to see us switching to diodes and voltage biases anytime soon because these things are so close to the quantum limit and have that very nice virtue of very high readout fidelity. They're also made in the same aluminum technology, so you can imagine implementing them sort of on chip in some bigger quantum scheme. So I'm pretty sure parametric is going to win the day. Past that, it's all kind of a question mark.
Okay. Any other? One last question? If not, let's thank Michael again, and also for your heroic effort to fill in for Vijay. So thank you.